Okay, I'll be speaking today about advances in MSM surface registration to bridge data across the BigBrain and FreeSurfer Human Connectome Project ecosystems. This is a collaboration between our lab and Alan Evans' lab and David Van Essen's group at WashU. So just a sneak preview of the data on the left. I'll go through that very quickly. And then let's move on. So the motivation is accurate surface registration allows a high-resolution histological BigBrain to serve as an unprecedented cross-validation tool. So if we achieve that accurate surface registration between BigBrain and a reference surface such as FS average, that allows us in one direction to transform MRI-derived surface atlases for use in BigBrain space, for example, to define ROIs in BigBrain. Or in the other direction, we can transform BigBrain cytoarchitecture for use in MRI standard space, for example, to validate those very atlases. The BigBrain surface presents several challenges to existing registration tools designed for use with MRI data and validated only within a particular software ecosystem. Some obvious differences: BigBrain is n equals 1 versus many subjects for average atlas. The BigBrain is extracted at high resolution versus standard 1 millimeter for FS average or FSLR. And quite obviously, it's more highly convoluted. There's more anatomical definition than any MRI-derived or population average surface. And even visually here quickly, we can compare FS average or FSLR. You can see it's incredibly smooth compared to BigBrain. So recently, we introduced preliminary versions of the first surface registration pipeline linking these reference surfaces via the Human Connectome Project's multimodal surface matching tool. This is from Emma Robinson's group, and there's been several versions so far. In 2021, our registration was included in the BigBrain Warp. And here we incorporate new tool developments in both the MNI and FreeSurfer ecosystems to optimize our pre-processing, leading to improved folding-based alignment, as well as reductions in distortion. Pre-processing. So our input is a civet-tessellated BigBrain white surface. We have a 2021 update from Claude. It's a standard 163K vertices per hemisphere. And the medial cut excludes the hippocampus, which is not standard for civet, but is more common for FreeSurfer and FSLR. We have a volumetric transform from histological to standard space. We use the HCP to drift space, which is somewhat analogous to MNI 152 space. We use a FreeSurfer tool, MRI's remesh, which was new in 7.1, to retessellate the white surface to 800K vertices per hemisphere, but don't worry, we don't stay at that very high resolution too long, just as long as we need to. We inflate the FreeSurfer tessellated white surface to sphere with modified FreeSurfer inflation tools. I can discuss these later if there's questions and if there's time. But of course, the question is why? Why this pre-processing? So the BigBrain inflates the sphere in a way that MSM expects. Following inflation of the sphere, the relative representation of the cortex versus the medial cut differs for BigBrain compared to MRI-derived FreeSurfer surfaces. And this is influenced by differences in surface area, as well as in hemisphere separation and tessellation approaches across software ecosystems. So let me show this briefly. Here's FS average to start, and you can see what it looks like. I might need my pointer here. On the right, how it inflates the sphere. And if you could try and take note of how wide the medial cut is, I'll show now BigBrain in histological space. So since it's so much more highly convoluted, there's more surface area, that's effectively compressing the representation of the medial cut once it inflates the sphere. So here's again its histological space. So next I'm going to show with the pre-processing. So you can see it inflates in a different way that's more similar to the way FS average is. So let's show FS average again, go back and forth a little. So those are more comparable. Okay, we already discussed this. So next, MNI tool SurfSurf Interpolate was updated in 2022, again, thanks to Claude, to obtain vertex correspondence between two versions of the white surface. So basically, you have two BigBrain surfaces of the exact same shape, just tessellated in different softwares. So original 7 tessellated 163K, and the FreeSurfer retessellated 800K. And this allows us to basically eliminate a previous extra registration step that we used to have, and now we can just borrow the FreeSurfer sphere at 163K using the obtained vertex correspondence. So there's no more 800K, we're back to a normal amount of vertices. We submit this sphere to the FreeSurfer Tool MRI's register. This is only to extract the affine for MSM registration, for MSM initialization. This is actually very analogous to what the HCP group does in their normal pipeline. Okay, so as I mentioned, we submit our 163K sphere that's already rotated from the affine from MRI's register, and then we add one more affine rotation. Normally this is done with focal depth, but that's really not sufficient for our problem. So we're using 2 landmarks that we define, and again, this is just a simple rotation of the sphere. There's nothing discrete or nonlinear going on here. So let me describe these landmarks. So just 2 single vertices in the anterior and posterior border of the medial cut. Here I show them on FS average anterior, BigBrain anterior, FS average posterior, BigBrain posterior, and again, this just get the rotation of the sphere in the optimal starting point. We don't use the landmarks again after this. Okay, so we're doing MSM direct from BigBrain to FS average. We concatenate to FSLR via the registration that already exists from the HCP group from FS average to FSLR. So right now we're focused on FS average. There's a multi-scale course-defined approach. We're progressing from left to right. We already discussed what happened to my laser. The wrong way? Oh, there it is. Okay. So we already discussed this. And then we submit that sphere to the focal depth for global scale. And then we submit the output of that as input to curvature for further details. So unless you're an MSM expert, you may not care about all of these configuration files, but I'll just touch on what's important. Again, we're progressing from left to right. And we're progressing from low to high resolution grids within each stage. Standard parameters are in black, modified parameters are in color. We use a trans flag across all the stages. This accounts for distortions of the previous stages. And the sampling grid and the data grid are set 1 level higher than default. So we use a landmark analysis. 18 landmarks or small clusters of vertices were identified in both BigBrain and FS average. I will show this briefly. It's a little easier to see on FS average because it's less convoluted, so hopefully you see little rainbow clusters of vertices. We did the same for BigBrain. And then following registration, the landmarks from BigBrain were resampled to FS average and concatenated to FSLR. The geodesic distance or error between the resampled and original landmarks was used to assess accuracy of our registration process. So first, also some qualitative visualization. So this is the brain tone atlas from the FAN group 2016. We've inversely projected it following registration from FS average to BigBrain. It's a little bit easier to see if you inflate the BigBrain surface. But we did not use the inflated surface for registration. It's just now for visualization. So sometimes you can toggle back and forth between FS average where it's defined. We could do this all day, but we don't have time. Claude made a nice little video, which is going to morph between the two. So right now it's FS average. It's morphing into BigBrain. Now it's going to morph slowly back into FS average around now. So these are a series of intermediate surfaces that he created, so we can see the progression between the two. Okay. And we can do the same for the MMP Glasser Atlas. So here it is again, projected to BigBrain from FSLR. We can inflate BigBrain. We can toggle between FSLR and BigBrain. We can play the video. So we're starting at FSLR. So it's slowly turning into BigBrain. We're going back toward FSLR. I'm happy to show different views of this at the end also, but that's all we have time for now. Okay, so that was all very subjective. This is more objective, our landmark accuracy analysis. Again, it's geodesic distance or error between the original resampled landmarks in millimeters. Our current pipeline is all the way on the right in green. So the current version of our modified MSM pipeline, again in green, yields reduction in mean error and in maximum error compared to our previous versions, which are orange and yellow, and I can describe these later if time, and also compared to standard default MSM with nothing adjusted. And importantly, all the outliers have been eliminated. I've circled them in red. So no more outliers. That's for the direct registration BigBrain to FS average. So as I mentioned, we concatenate to FSLR. It's a little different than the past where he did more direct registrations. But even with this concatenation, the story remains the same. We still have reduced mean and maximum error compared to our previous versions, compared to standard MSM in red. And again, the outliers are eliminated. There's an additional thing to note that we have a little trade-off here. So we believe it's worth a slight elevation. There's a few data points here that had very extremely low error, and they go up a little bit, so we lose some there. But the trade-off is that we bring down these really high errors. So the data is now more compressed in a reasonable range. Distortion. As benchmarks, we compare distortion values across current and previous versions of our modified MSM pipeline to those that were reported by Robinson's group on a subset of the HCP cohort. So our data is the green, yellow, orange, and other data is all the other colors. There's also a little dotted line, vertical lines you can see. So first, maximum distortion for the current version in green is reduced compared to our previous versions, orange and yellow, in particular for shape distortion, as you see on the right, and now closely approximates the HCP data MSM SOLC benchmarks, which are in reds, left of the dotted line. Mean distortion for the current version, green, is slightly lower, but pretty similar to our previous versions, orange and yellow. And although it's not as low as the HCP data MSM SOLC benchmarks, again, reds, left of the dotted line, it remains lower than that of FreeSurf for magenta, which is very high everywhere. So that's a little bit of a sanity check at least. If lambda, the regularization weight, is set too high, a vertex cannot move far enough. So great, you'll get low distortion, but also low accuracy, which is not great. But if, on the other hand, if you set it too low, the vertex can move far enough, sure, but it may also move implausibly too far, and this would result in moderate accuracy but high distortion. So our ideal balance is somewhere in between the two extremes. We might need to tolerate some reasonable amount of distortion in order to achieve high accuracy. Conclusions. Our modified MSM pipeline yields improvements in alignment of folding-based landmarks relative to standard MSM and to our previous versions. Reduction in mean and maximum error, elimination of outliers, reduction in distortion values, and with improved precision, any surface atlases or derived data from in vivo imaging in FS average or FSLR space can be projected to compare against corresponding set of architectural properties defined in BigBrain and vice versa. So upcoming work, we wish to incorporate BigBrain set of architecture maps and HCP FSLR multimodal maps into the pipeline. So there's a debate of folding versus functional alignment, just improving one worse than the other. So the HCP group would say that by improving folding alignment, you might have detriment to functional and vice versa, but we'd like to try it out and see if it helps or hurts. New MSM was just released. Emma Robinson announced at HBN this summer, and I've already started playing around with it. And of course, we want to adapt all of this for BigBrain too. So thank you. I'm open questions or comments, and thanks to funding agencies.
Okay, we are a little low on time, so I would say burning questions only. If we have any burning questions.
I think this is a fast question. If so, you could. If not, you could ignore. You were using the corpus callosum as your AP landmark, setting that. So in stereotactic coordinates, the anterior commissure, posterior commissure are traditional. Can you tell us in a few words, otherwise we discuss after, why you chose the corpus callosum rather than those two commissures?
I'm sorry. I know it's somewhat analogous, but I'm doing it more on the cut of the software, I guess. So maybe you can rephrase the last part of your question.
I don't want to make it longer. Stereotactic coordinates, if you're doing animal surgery, you use the anterior or an atlas, anterior, posterior commissure. But you were using the corpus callosum, which would be a little bit more variable, I would have imagined.
I'm assuming that's because it's more of what is visible on the surface has been extracted. So I'm not working in volume space, I'm working on the surface. And honestly, it's a little bit of trial and error. I was seeing where the problems were creating registration, and by anchoring at this point in particular, I was able to get in a starting point to overcome.
So you're employing a wider context.
Yeah. Thank you.